Welcome back to the deep dive. I was driving the other day and my kids were in the back seat and they started playing that classic game, 20 questions.
Oh, yeah. The ultimate road trip survival tool.
Exactly. And it struck me that you always start with the same opening move, to narrow down the entire universe. You ask, is it animal, vegetable, or mineral?
Right. It pretty much covers everything.
It does. And we use that word mineral all the time. I mean, I take my vitamins and minerals in the morning. We hear about mineral rights on the news. But looking through the research for this, I had a bit of an embarrassing realization.
What's that?
I think I've been using that word wrong my entire life.
Well, you and pretty much everyone else is one of those terms that has a loose everyday meaning, but a brutally strict scientific one.
So that's our mission today. We are going to unpack the ground beneath our feet. We need to separate minerals from rocks.
Because there is a massive difference.
The huge difference. And then we're going to zoom all the way in to the atomic glue that holds our planet together.
And this isn't just about, collecting pretty stones. This is the detective work geologists use to figure out what the world is actually made of.
And why it matters to us. I mean, practically every single manufactured object in this room relies on minerals. I'm looking at my pencil. That's graphite.
The talc in cosmetics, the silicon on the computer chip recording this.
Right. The silicon is sourced from quartz. And our hunger for this stuff, it's been leaving a mark on the planet for a lot longer than people realize.
A lot longer.
This was the first thing in the notes that really it stopped me in my tracks. We usually think of pollution as this modern thing, post-industrial revolution.
Right. Smokestacks, burning coal, that sort of thing.
But the archaeological evidence, it tells a totally different story. Researchers found these records in Greenland ice cores. They show a massive spike in atmospheric lead pollution. But the date, it wasn't 1850. It was from 500 BCE to 300 CE.
The Roman Empire.
The height of the Roman Empire. Their smelting of lead and copper was so massive it polluted the air thousands of miles away.
It's incredible. Proof that we've been manipulating these building blocks on an industrial scale for millennia. So to understand that, we have to define what they actually are.
Okay, let's do the checklist. The research has this strict 5-part test. So if I just walk outside and pick up a random stone, does it pass?
Probably not. And that's because rock and mineral are not synonyms. So requirement number 1, it has to be naturally occurring.
Okay, so a synthetic diamond made in a lab.
Not a mineral. It might be chemically identical, but if a human made it, geologically, it doesn't count. Nature has to do the work.
Got it. Okay, requirement 2, generally inorganic.
Right. This is where we separate biology from geology. So think about sugar. You can grow beautiful sugar crystals.
Right, they're solid, they sparkle.
But sugar comes from plants. It's organic, so not a mineral.
But the notes mentioned a gray area here that confused me. What about seashells? A clam makes a shell from calcium carbonate. That's a living thing.
It is, and that's the big exception. Marine animals secrete calcite, and because that calcite ends up in the rock record, like the White Cliffs of Dover, geologists generally accept it. But as a rule, no organic carbon chains. Coal, for example, is not a mineral.
Because it comes from ancient swamps.
Exactly. It's a rock, but not a mineral.
Got it. So number 3 seems the simplest. It has to be a solid.
Correct. No liquids, no gases, which leads to the classic gotcha question. Is ice a mineral?
Oh, my gut says no, it's just water.
Liquid water isn't.
Yeah.
But freeze it. Ice is naturally occurring, inorganic, solid, and this is the key, it has a crystalline structure. So yes, ice is a mineral.
So does that mean a glacier is technically a rock?
A glacier is a rock. It's
Yeah.
a huge mass of the mineral ice.
Wow. An igloo is a stone fortress.
In the eyes of a geologist, yes.
Okay, you just mentioned crystalline structure. That's number 4.
And this might be the most important one. The atoms inside have to be arranged in an orderly, repetitive pattern, not just jumbled together.
Which brings us to obsidian. Volcanic glass. People used it for arrowheads for years. It's natural, it's hard.
But it's not a mineral.
Because of how it forms.
Exactly.
Yeah.
Lava cools so fast the atoms don't have time to line up. They just freeze in place in total chaos.
Mm-hmm.
So obsidian is a solid, but it lacks that internal order. It's a mineraloid.
Frozen chaos. I like that. Okay, and the final requirement.
A definite chemical composition. You have to be able to write a formula for it. Quartz is always SiO2. 1 silicon, 2 oxygen atoms. Change the recipe, and it's a different mineral.
Okay, so natural, inorganic, solid, crystalline, and a specific recipe. But let's go back to the rock versus mineral thing. I feel like most people use them interchangeably.
They do, but it's like Think of a chocolate chip cookie.
Okay, now I'm hungry.
The minerals are the ingredients. The flour, the sugar, the chocolate chips, those are the pure substances. The rock is the cookie itself. It's an aggregate, a mixture of different things all stuck together.
So if I pick up a piece of granite,
You're holding a rock. But look closely. You'll see pink specks of feldspar, glassy gray bits of quartz, black flakes of hornblende. They're all jammed together, but they're still separate minerals.
can you have a rock that's made of just one mineral?
You can. Limestone is the classic example. It's a rock, but it's made almost entirely of just one mineral, calcite. But usually, rocks are the team, minerals are the players.
That helps. But to really understand why they act the way they do, why gold is soft and diamonds are hard, we have to go smaller. We have to talk about atoms.
We do. And I promise, no high school physics lecture, but we need the basics.
The source material used a great analogy for the scale. We picture the atom with electrons orbiting right next to the nucleus, like tiny planets.
Yeah, and that's totally wrong. It's almost all empty space. Imagine the nucleus, the protons and neutrons, is a baseball on a pitcher's mound.
Okay, a baseball in the middle of a stadium.
On that scale, the electrons would be the size of a single grain of rice, and they'd be way out in the cheap seats.
So all that space between the pitcher's mound and the cheap seats is nothing.
It's just empty space. It's wild. But those little grains of rice in the outermost row, the valence electrons, they're the ones that matter.
The social butterflies.
Exactly. The nucleus is stable, but the valence electrons are the ones that interact, form bonds, and determine everything.
And before they start bonding, where did all these atoms even come from?
My favorite fact in all of science. Aside from hydrogen and helium, every atom, the iron in your blood, the calcium in your bones, was forged inside a massive star that exploded as a supernova.
We're literally stardust.
Stardust that clumped together to form Earth.
So these atoms are here and they start bonding. Why?
Well, they want stability. And for an atom, stability usually means having a full outer shell of electrons, usually 8. It's called the octet rule.
Yeah.
If they don't have 8, they're unstable, so they bond to steal, share, or borrow electrons to get to that magic number.
And how they do that bonding makes all the difference. Let's start with ionic bonds, the opposites attract method.
This is basically theft. One atom gives up an electron, and another atom takes it.
And the classic example is table salt, or halite.
It's pure alchemy. You start with sodium. It's a soft metal that would explode in water and poison you.
Not a good snack.
Then you have chlorine, a toxic green gas used as a weapon in World War I.
Also not a good snack.
But sodium has one extra electron it wants to get rid of, and chlorine needs just one to be complete. So sodium gives its electron to chlorine, sodium becomes positive, chlorine becomes negative, and they snap together like magnets.
And you get sodium chloride, harmless, tasty salt.
2 deadly things become essential for life. Just by swapping one tiny particle, that's an ionic bond.
Okay, then we have covalent bonds, the sharing model.
Right. Instead of giving an electron away, the atoms get close and share them. It's a much, much stronger bond. The carbon atoms in a diamond are held together by covalent bonds.
Which is why they're so incredibly hard.
The hardest.
But the third one, metallic bonds, is the one that really blew my mind.
This is exclusive to metals like copper and gold. The atoms pack together, but they let their valence electrons go.
They just release them.
They detach and form this communal sea of electrons that flows through the whole structure. They don't belong to any one atom, they belong to all of them.
And that sea is why electricity works.
Precisely. Electricity is moving electrons. In a salt crystal, electrons are locked in. In a copper wire, they're free agents. You push them in one end and they flow out the other.
It also explains why metal is malleable, right? If I hit a rock, it shatters. If I hit gold, it just dents.
Yes. In a salt crystal, if you shift the atoms, you might force 2 positive ions next to each other. They repel violently, and the crystal breaks.
But with metal.
The atoms are swimming in that fluid sea of electrons. The sea acts like a cushion. The atoms can slide past each other without breaking the structure.
That's amazing. Okay, so we've got the definition, the atomic glue. Now, the detective work. How do geologists actually identify this stuff?
It's a toolkit of properties. Some are diagnostic, meaning they tell you the truth. And some are ambiguous. They're there to trick you.
Let's start with the big trickster, color.
Color is the biggest trap. You see a purple crystal, you assume it's amethyst. But it's just quartz with a tiny impurity.
And fluorite is the worst offender.
Total chameleon. Purple, green, yellow, pink. It's all the same mineral, just with tiny chemical accidents that change how it absorbs light. Never trust color alone.
So what's the truth teller?
The streak.
The streak.
You take the mineral and you rub it on a piece of unglazed porcelain like the back of a tile. The color of the powder it leaves behind, The streak is incredibly consistent, even when the mineral's surface color changes.
Interesting. So something shiny might leave a dark streak?
Usually, hematite can look silver or rusty red, but its streak is always a reddish-brown. It cuts right through the disguise.
Okay, let's talk luster. That's just a great word.
Luster is just how light reflects off the surface. The first big divide is simple, metallic or non-metallic.
But non-metallic is a big category.
It is, so geologists get pretty poetic. Vitreous is glassy, like quartz. Earthy is dull, like dirt. Pearly has that sheen, like the inside of a seashell.
The notes mentioned greasy.
And it's accurate. Minerals like talc and graphite actually look and feel like they're coated in oil. If you touch graphite, it's slippery.
Okay, let's talk about the big one, hardness. The Mohs scale.
A relative ranking from 1 to 10. Talc is a 1, the softest.
The stuff in baby powder.
Right. And diamond is a 10, the hardest natural substance.
But in the field, you don't carry around a full set of 10 minerals. What are the common tools?
Your own body. Your fingernail is about a 2.5 on the scale. So if you can scratch a mineral with your fingernail, you know it's really soft, like gypsum, which is a 2.
And if it scratches your nail?
Then you try a copper penny, which is a 3.5. Or a piece of glass, which is about 5.5.
So it's a process of elimination. If I find a clear crystal and it scratches glass,
then it has to be harder than 5.5. So it's probably quartz, which is a 7. Calcite, which looks similar, is only a 3. It wouldn't scratch the glass.
simple but really effective. I also want to touch on crystal shape or habit, because if you let these things grow, they form these perfect geometric shapes.
It shows you that internal atomic order we talked about. Halite and fluorite grow as perfect cubes. Magnetite forms octahedrons.
And garnets are dodecahedrons, 12 perfect faces.
It's incredible.
The word crystal itself has a cool backstory.
It comes from the Greek kristallos, which means ice.
Right. The ancient Greeks found quartz in the Alps and thought it was water that had frozen so hard it could never melt.
Which brings us right back to our ice discussion.
It really does. Okay, one last tool. Cleavage versus fracture. This is about how a mineral breaks.
Exactly. If you smash it and it shatters into random curved pieces, that's fracture. Quartz does that.
And cleavage?
Cleavage is when it breaks cleanly along flat planes of atomic weakness. Think of mica. You can peel it into those impossibly thin, perfect sheets.
Okay, so we've built the whole picture.
Right.
From the definition down to the atomic bonds and back up to the detective's toolkit.
That's the core of it.
But let's zoom out for the so what. Why does this matter to someone who isn't a geologist?
Because these aren't just rocks. They are the operating system of the planet. And for us, for human civilization, they're everything.
We name our history after them.
The Stone Age. The Bronze Age, that was just humans figuring out how to mix copper and tin minerals. Then the Iron Age.
And today,
We are squarely in the Silicon Age. We take quartz, purify the silicon, and build the chips that run the entire global economy. It's all just a massive mineral processing engine.
it really puts that pencil in my hand in a new perspective. Before we go, I want to leave everyone with one image. We talk about crystals, but we picture something small.
Oh, I know where you're going with this. The Golden Giant.
The golden giant. It's the Topaz in the Smithsonian, and the picture is just unbelievable.
It's a 22,892 carat golden yellow topaz.
22,000 carats.
It weighs 10 pounds. It's the size of a car headlight.
Just imagine that, a single perfect crystal grown by the earth that weighs as much as a bowling ball.
It's humbling. It's a reminder that the earth produces these things on a scale that's just hard to comprehend.
So next time you salt your food or drop an ice cube in your drink, take a second. You're holding an orderly crystalline structure forged in an exploded star and held together by the fundamental forces of the universe.
Definitely worth a second thought.
Thanks for diving in with us. We'll catch you on the next one.
See you then.